Welcome to my talk about the binary whisperer. I'll be speaking about, not about whispering magic, but about a tool that I wrote, which intends to ask binaries about their intentions. So I got a bit bored with analyzing binaries. I wanted to have a tool which analyzes binaries for me and presents me the finished results. And today I'll be explaining how that is supposed to work. Short note about myself. My name is Marion. I'm a security researcher, currently independently contracting, and my main focus is on analyzing Windows malware. So I'm a reverse engineer, and I like to take things apart, as you just heard. Malware analysts. So what is it that I do? I spend my days staring into binaries and finding out what their behavior is, what they were written to do. And there's a lot of issues to find there, like binaries are big, binaries are complex, binaries are complicated, they take up a lot of your time, and the biggest issue that I have with that is that I'm actually a lazy person. Most of us binary analysts, we're lazy. Like, we don't actually enjoy staring into binaries for hours and days and weeks. So we really would like to automate our job, to have an easier life, get stuff done quicker, and have more spare time. On the other hand, malware analysis itself presents us with a lot of issues. So despite the general belief that malware is evil and complex and sophisticated and out to get all your goods and all your money and eventually kill you, most malicious binaries are not that complex as one might think. So today we see a large number of new malware binaries coming up every day. Like, some vendors say it's up to 100,000, 200,000, 500,000, whatever, like large numbers of binaries. But what most people do not recognize and don't consider with these binaries, that they're very repetitive. So if you have 100,000 malwares per day which are produced anew, you can suspect that 90% of these binaries are not actually freshly written, or I would expect more, like 95% of these binaries are not fresh malware, but they're like code that has been copied from a different code base from before, and is very repetitive in how it is written and what it does. So as a binary analyst, when you stare at a binary that you haven't seen before, chances are you see something that you've seen before. So code is being reused. Also, when we look at these binaries, most of them are not very sophisticated. Most of them are out to reach their goal quickly and efficiently, but not in a very, very complex manner. This is because most of the malware authors which we see work today, they are not actually software developers, but they are script kiddies who learned to code, like basically like I did. So when I code, I go to Stack Overflow and search for a solution for my problem, and I take that code and I use it. So that's how most of these malware authors write their binaries. So we don't see very much innovation from that side. Finally, another question: wouldn't it be nice to just have a tool which takes this boring job of looking into binaries from you and tells you at one glance what a specific binary is doing? This is what I was focusing on with this research. This comes with some trouble. Automated analysis currently faces a lot of issues. Basically, we see two different fields of automated analysis, which would be the static side and the dynamic side. So in static analysis, if you ever tried to reverse engineer malware, you can see that a lot of it's packed, a lot of it is obfuscated, a lot of it tries to hide what it actually intends to do. There is virtualized code which presents itself as bytecode, which is very hard to disassemble and in the end to analyze. We see a lot of means to hide the actual intentions of a binary, which includes obfuscation of strings or dynamic API loading, which is not necessarily helpful for the binary analyst. On the other side, a lot of analysis systems today aim for dynamic analysis. So we see a lot of sandboxes, and not many of them are actually really high-end analysis systems. So one of the problems that sandboxes face is that, of course, they're easy to detect and they're easy to evade, and malware can hide its functionality from the sandbox and whatnot. But the bigger problem that I see with sandboxes is that they're actually fairly limited in the areas of the binary that they can see. So if you load a sample into a sandbox, you are actually relying that this sample will execute when you double-click it, like when you start it, and it will exhibit all its functionality, which is almost never the case. So there's a lot of cases where sandboxes actually do not see the full spectrum of functionality of a binary. Clicker, click. Right, so a common sandbox is fairly limited. Here I brought an example of, for example, you imagine a standard RAT, a remote access Trojan, which is a Trojan which infects a system and then gathers information from the system, like, for example, gathers keystrokes or gathers screenshots or files from the file system and sends them to a remote server. This would be a common RAT. Usually, these RATs come with, clicker, right. They come with a protection layer. In the next step, they come with a setup layer where they infect the system and set up their own binary on the infected machine. Then they might call home, they might contact their remote server, and from this step on, things go sideways. So then you have infected the system, you have your RAT installed there, and the RAT is waiting for input from the remote server. Even if the remote server is still up, chances that this remote server is going to send all its command at the same time to the bot, so the bot can exhibit all its functionality, are really, really low. I've never seen that happen, seriously. So sandboxes in that situation are just not able to show you all the things that this RAT could do. And finally, the last point, why I'm not really a big fan of sandboxes, is that they were actually written, they were actually designed to analyze malware. But what if the analyst gets a task to analyze benign files? So sandboxes in almost all cases are very, very useless when you try to prove that the sample is not malicious. These use cases come up quite often if you work in incident response and you get like a set of binaries and you have the suspicion they're malicious, and your customer is asking you, so this is one of the binaries we use in our critical systems. Can you please prove me that this was not compromised? And then you put up a contract asking him for a lot of money, because this is going to take a lot of time. Finding out something is malicious is fairly easy compared to proving that something is not malicious. So yeah, we do not have any means of automation in that sense. So what did I set out to do? I set out to put a tool together which would statically analyze a given binary with the help of graphs. I would use the call graph of a binary to get like a bigger layout of that specific binary, and then search for API calls and strings within that binary to fit it into my graph to see where are the areas of that binary where the malicious things are happening, the malicious behaviors, and how could I see these behaviors at one glance. Why did I use graphs for that? Well, graphs are a great data structure. That's actually the point. They are a data structure, and at the same time, any binary is a graph. Any binary which is written with a functional language shows functions, and these functions call each other. So there you have the call graph, and at the lower level, you have the control flow graph, which means the basic blocks within each specific function. So yeah, with my project, I was focusing on the call graphs and the strings and the APIs, which is fairly simple. Now let me tell you why I think this is actually necessary. So talking to other researchers, I got a lot of wouldn't you think that samples are packed or obfuscated and you can't actually see any of the things that are in there? And I have two answers for them. Like, first of all, you can unpack your samples. That's what we do. Like, we're malware analysts, we're able to unpack samples, and then you can still do static analysis. And on the other side, a tool which looks at the call graph and tells you that something is packed is actually valuable information. And the third point of why I think this makes sense is that most of the malware that we see in targeted malware research is not actually packed. So earlier in 2016, I conducted some research on a sample set of targeted malware. That set was about 6,000 files big. So we had 6,000 samples where we had reason to believe that they were used within targeted attacks. And to compare that, we gathered a sample set of about the same size of benign samples and of randomly malicious files. And these statistics, I believe you cannot see the numbers, I can't either, but I can tell you that for the targeted and the benign set, the numbers on the left side are about 4,500 to 4,700 samples big. And on the random set, the left side of the bars, this is about 1,700 samples. For this research, I would evaluate the samples based on indicators which I considered indicating runtime packers. This is just a method of evaluating the samples. So this is not a runtime packer detection. But based on heuristic tests, I can say that most of the samples I picked out of the supposedly packed samples were actually packed. And the samples without any packer indicators were actually not packed. So from this test, I could see that large parts of the targeted NT-benign sample set didn't show any indicators of a runtime packer, and from the random sample set, a lot of samples actually did. So based on that knowledge, I started further research on the targeted sample set to find out whether I could extract behavior from that targeted sample set, which would tell me more about the content of these binary files. Now finally, why? Why did I do this? What was the actual purpose? And you will not believe, if you go to Google and search for a meme which contains the word why, this is the only slightly funny picture you can find up there. What were my goals? So as I said, I wanted help in static analysis. I find myself often in situations where I get 5 to 10 to 15 samples, and I get the question find me the malware in there, quickly, like yesterday. And this is why I wanted a tool which helps me to get a quick overview of what these samples were about. Are they packed? Are they not packed? Are they obfuscated? Do they exhibit any APIs? Do they load a GUI? Do they look like they could be a keylogger? Do they have any references to registry keys which tell me they could care for persistence? This is the information I wanted to get quickly. The tool should be easy to handle. It should be extendable. Should be open source. I didn't want to spend any money on that. And that's why I built my binary whisperer. On the other side, I had a set of non-goals. What I was not after was big data. I didn't want to do binary clustering. I didn't want to do machine learning, for I don't actually like machine learning that much. I like to throw machine learning at things. I didn't intend to do binary diffing, and I'm not a mathematician. So I used graphs, but I'm not into higher math, so don't expect any formulas here. Yeah, that were the goals, a simple tool. Finally, what I get out from my tool looks like this. Just to give you an idea, so this is a graph from a binary. You can see the different nodes. The nodes relate to functions. I'll explain the coloring and the content of the nodes a little bit later. But you can see inside the nodes, these are the strings and the APIs that are being handled within these nodes. How did I get there? How did I get to these graphs? Yeah, so I used Radari 2. For those people who haven't heard about Radari before, Radari is a disassembly framework. So with Radari, you can, based on the command line, disassemble about any binary format that humankind has seen before. If Radari fails to disassemble a specific format, the authors of Radari will happily implement that functionality for you. So they're really eager to support as much as possible. Also, you will not believe when you tell people, yeah, I built something on top of Radari. How many people ask you, why? Why the hell did you do this? Radari is an open source tool. It has been developed for 10 years now. Their developers are really motivated, really eager, produce a lot of code, and their code also contains quite a bunch of bugs. The people from Radari are the fastest bug fixers I've ever seen. I've once reported a bug through their IRC channel and got an answer immediately, yes, I'm going to fix this. And 5 minutes later, I got the yeah, update now, it's fixed. So they're really, really quick. But still, Radari is not actually software which I would recommend to use in production mode. But for writing a tool like I did for simple binary analysis, it is the currently best option, the best solution that is out there. And I would recommend you to check it out. What was my reasoning? Why did I go for Radari? As I mentioned before, it's one of the few disassembly frameworks out there. Actually, the most evolved disassembly frameworks right after IDA Pro. Next to IDA Pro is the only disassembly framework which is actually free. So I used it because, of course, I wouldn't have to pay for my own Radari installation, but also because I have the option to, once my tool is ready for batch analysis, I can put it up on a cluster and run 500 instances of it at the same time without paying for a license. As I mentioned, there's great support. There's really quick bug fixes. There's a very active community where you can ask for new features. And most importantly, Radari is easily scriptable. It's command line based. If you ever try to script IDA Pro, you can understand my pain there. If you ever try to operate IDA Pro in batch mode, you will have had a lot of fun with the GUI popping up and down, because there's no mode that I know of where you can script IDA Pro without having that GUI coming up and down. So anyway, that's why I really liked Radari. Also, because you have this mode where we can analyze entire binaries. Like with either Pro, when you load the binary in there, either Pro starts the analyzer and disassembles your binary and finds functions and finds global variables and finds structures and defines all that for you. Radare does kind of the same thing. So what you have there is a fairly well-functioning function detection. You can have the cross-references to the functions, which you need for the call graph. You can detect symbols of Windows APIs within the functions. You can detect cross-references of strings and extract the strings within the binary, and of course, you get basic P information. And another feature, which I thought very convenient, was that if you actually pipe Radare Pro through lolcat, you get rainbow-colored disassembly. I spent a lot of time staring at that rainbow-colored disassembly. At this point, a lot of thanks to the development community of Radare, and as I said, like my approach to Radare was joining that community and asking questions. There's many people ask me, how's the learning curve for Radare? Like, how did you learn that tool? I didn't. So I still have no idea how to properly instrument Radare. Whenever I need to change something on my tool, I ask the Radare people, and whenever you ask these people a question, they shoot back a command line. Whatever you ask, you get back command lines. And then you can use these command lines for your own tools, which is pretty neat. So yeah, I don't actually think there is a learning curve per se. Finally, the tool is called Graffiti because I'm very bad in naming things. So I thought it's about graphs, so I call it Graffiti. It has some rather small modules, which basically do nothing more than getting that call graph out of IDA Pro and parsing that call graph, fitting the API calls and the strings into the graph. And then it can plot the graph, it can analyze the graph with some predefined algorithms, and it can dump the graph into a Neo4j graph database. The code is published under MIT license. It's published on GitHub. You can find the link on the slides, and I'd be happy to get feedback to the tool. Don't expect like a super professional code base there. As I said, I'm not a software developer. I like Stack Overflow a lot, and the code in there looks just like that. But you're welcome to have a look and improve and use the code as you like. All right, what does this tool do? I was out to do binary cartography. I don't know if you can see that graphic here very well. It's like a world map where you can see a basic description of the different parts of the world. For example, in Canada, it says shitty music and bears. America has freedom and Jesus. And so it goes on to describe the different parts. And that's basically what I wanted. So I wanted a map of the binary with descriptions for the different parts, so I wouldn't have to analyze every part in detail. As I said, this worked with function call graphs. So I would run a parser to detect all the functions, look for the cross-references, and this way build a graph of my functions. That's basically based on the references to function offsets. Next to that, looking at cross-references, I got a lot more data. For example, references to code which was not related to a specific function. So I would have references like into the nothing of code that wasn't parsed as a function, which for me turned out to be a good metric for obfuscated code. So if the function detection would fail to find code at a specific offset which was referenced within other code, I could suspect code to be there. I could suspect that there should be a function there, and if there was no function, that would serve as a metric for actually obfuscated code, which was not possible to parse for Radare 2. Also, I figured out that calls from the code section, which terminated into memory spaces outside of the code section, would be references to global variables. And if you have like a call reference to a global variable, that's a good indicator that there is dynamic API loading or dynamic initialization of these memory locations, which would later on be functions at runtime. So these are like metrics that one could use to say this is obfuscated, this uses dynamic API loading, and so on and so forth. A little bit more about the metrics later. Finally, as I said, the graphs, their nodes would be the functions, and their function calls would be the edges. So anything that would reference the local code section would be an edge. And also I tried to resolve indirect function calls. Like for example, if you have a thread handler or a hook handler, then my parser would try to find like an edge where there was no direct cross-reference, no direct call to that code offset. Also, bit of an issue trying to find all the strings within the binary that would give me information. If you have analyzed binaries before, you know that like parsing for strings is a good start to look into the binary, what is happening in there. If it's not obfuscated, you might get a clue about CNC commands, you might get a clue about error messages, or maybe just comments or strings that the author forgot inside of the binary. So here's a list of fairly beautiful strings. A bigger issue with the strings is, though, that when you parse for something that looks like a string, you also get a lot of garbage. So you will not only get the useful strings that are really used within the binary, but usually these strings parsers, they will just interpret everything that looks like an SC character chain as a string and give you that as output. Because these tools are stupid. They have no way to interpret the characters that they see to say, like, this is a valid string or this is just garbage. So what comes in here for the string parsing, of course, is a set of evaluation methods. Most of all, the cross-references. So I would say if I have something that is recognized as a string, this is a valid SC character chain, which was referenced within a function. So that offset would pop up in a function. I would say this is like a string that is being referenced. This is kind of like sorting out strings which are not actually referenced within the binary. That's high likely to be garbage. Also, somewhat experimental so far on evaluation method on character frequencies. What's a character frequency analysis? Any language, for example, the English language, every character that the language uses has a certain frequency within text. There's something, there's tables you can look up online. So for example, character E is the most frequently used character within the English language. And every other character also is assigned a frequency with which it is used within English text. So with these character frequencies, you can evaluate a string of how likely this string, with the characters it contains, is an English string. In practice, this works well for longer pieces of text. With a binary, you have the problem that a lot of strings are rather short, and on rather short strings, this frequency analysis tends to fail as well. So this is why you need this combination of the cross-references of SC strings and of the frequency analysis to actually get good results out of the strings. Finally, sometimes it happens that binaries would not use like references to one string after another, but would use lists of strings. This happens a lot when you see a CNC command parsing function, like all the commands that the remote server would send to the binary. The parsing function would then probably not handle each command by itself, but like try to parse the input from the remote server and match it with the specific commands that the binary knew. So in these cases, very often there's a list of strings within the binary. And all you see then is the reference to the first string, and you have to find the rest of the list to get like a full picture of the commands that you want to detect. So this is why I perform some simple string list detection, which is basically finding a string, and if after that string there comes another string, I will start searching for this consecutive list of strings within the binary. Finally, I will go on and fit these strings to my graph. So then afterwards, you have these bubbles full of information that show you what this specific function is intended to do. All this together, what do the strings help us? Well, first of all, we get the picture of the functionality or like of the usage of these strings in the binary. But also, if you think about a larger sample set, you could try to see commonalities between the different strings within the binaries. One nice example. Yeah, right. What's the information you can gain from strings? One nice example were a set of files that I have looked at a while ago, where the authors were using the English language to describe their strings in the binary, and they wouldn't be so proficient with their English. So you saw typos within these strings. And the typo within like a CNC command or within a string used within the binary is great. It's like if they ever happen to copy-paste this code base, and they highly likely copy-pasted the typos as well. And even if the code base changes, if you still have this typo within the string, you can definitely tell like this was the same guy with a very high probability. So this is why matching strings with each other is actually great. Next point, the APIs. So in this screenshot, you can probably not read this. This is the output that Rodari gives you with the dedicated symbols. Symbols in this case describe Windows APIs. So I would search for the different APIs exported by Windows DLLs and try to fit these APIs with the graphs. This again worked with cross-references, so I could add them into my nodes. And the problem on that section were indirect calls. So very often you would find a symbol tagged as like call create file, then you would know, like right here, this function is being called. But what, for example, if a symbol was being loaded onto a global variable, this global variable was then handed down through the function or being called at a later position within the binary, then you would have no idea with cross-references which API was actually called. So I tried to parse out indirect function calls to find APIs that had been called without direct reference to their symbol. Next one, yeah, finally. There's one thing that IDEPRO does that Radari didn't do, which I had to do manually, which is thunk pruning. For binaries that are compiled with Visual Studio, very often you see function thunks within the binary, which is nothing but a linking function between the actual function call and the import table. So you will see a lot of these thunks in there. When I started parsing my graphs with Radari, I got like huge graphs because I saw all these thunks in there, which were the cross references. So every API call would generate a new node within the graph. So I had huge graphs. By pruning out these thunks, the graphs got a lot sleeker, a lot smaller, and a lot nicer. Also, of course, a big problem in that sense is dynamic API loading. As mentioned before, like if there's one function loading all the APIs dynamically, storing them into global variables, and afterwards within the binary you would see nothing but references to global variables. The parser would have a hard time finding its way back from the global variable to the actual initialization. So that was a bit of a challenge. On the other side, though, if we see dynamic API loading within the binary, if it's small scale, this is still like a usual Windows binary behavior. I know developers do that sometimes. But if you have like no API references at all within the binary, and you see dynamic API loading, you could conclude that like all the APIs are being loaded dynamically, which is something to catch your suspicion. Finally, indirect function calls. This also turned out to be a bit of a challenge. For example, if you have like a thread that is being created, you have the thread handler being handed over to the create thread function, and you do not actually know like where in the binary this has to be located. So I was searching for these indirectly handled functions in the sense that I could fit them into the graph. So this is not a call reference, right? This is an indirect reference to that function, but I still wanted this to be represented in the graph. So then I went on to do a top-down approach. I was searching for functions like create thread or create Windows hook to search for their handler functions, to be able to tag them appropriately within the graphs. So I just go up in the disassembled code to search for the cross-references of these specific functions. On the other hand, what I still didn't see were handler functions which were not handled by a specific API which I knew, which I would search for. So I came up with a bottom-up approach where I would search for nodes that wouldn't have any cross-references yet. So I would search for hanging nodes. I would search for cross-references of these functions within the code. So this was not actually a call reference, so I wouldn't have a call to that function, but I would just see that function offset being referenced somewhere within the tree, and I would add an edge for this specific function for the graphs. All right, another issue that I faced were compiler settings and optimizers. Like you can consider that a binary which is compiled with different settings within Visual Studio will produce completely different graphs in my parser, because the function structure changes. Some functions, some nodes are being created more or less depending on the compiler settings that are being used. And my goal actually was to ignore most of that. So I wanted as little data as possible to gather as much information as possible. So I did some testing with the actual Visual Studio compiler to generate different binaries from the same source code. And with the graphing tool, I got results like that. Like you see this graph being changing with the different settings from time to time. But what you always can see is this big bubble quite in the center, which is like the single function that the code contained. So this was the thing that I wanted. So for actually evaluating my graphs properly and finding functionality properly, I had to come up with different metrics that would help me find these major nodes, like find the functionality within the binary. A little bit more about that in a second. What did I get out of my tool? There's 4 different things that I wanted to produce. Like as I said, I was searching for behavior. One of the points that I wanted to get out from the tool was visualization. You saw the graphs before, like a picture of my binary, which helped me like spot things quickly with the free eye. Also, I wanted to have something that automatically extracted behavior from me, and I wanted to have metrics to evaluate the binary. I wanted to say, this is packed, this is obfuscated, this is neither packed nor obfuscated, but doesn't show API calls. This is a very dense graph with very few APIs. This is a very small graph with very many strings. Metrics like that help me evaluate the given binary. And finally, I added a module to persist my data into a GraphDB. All right, back to the case study. So this is the graph you saw before. Actually, that name is disappearing. It's called Redzip. I don't actually have any deeper understanding of that malware. It's just posed as a very nice example because it produced a small graph that was very nice to read. If you want to have a look at the samples which I used for these specific case studies, you can look them up at the GitHub repo of Citizen Lab. They have like a list of target malware there, which they saw in their investigations. That's what I used to start my research. So from this graph, you can see there's a lot of nodes, some bigger, some smaller. There's some blue, some pink, and some green nodes. The blue nodes actually, I tagged, for example, DLL exports as blue, and I tagged handler functions, as I said before, like from create thread or from Windows hooks as green, and everything that's pink is a normal node. All the white nodes, you can barely see down here in the left side corner, are nodes without any references to APIs and strings. Now, what can you see in the graph? So this is a nice binary because it really exhibits a lot of things it has to show. So you can see this one callback function from a create thread call. And you see in there a list of CNC commands. I'm not sure if you can read this. They're saying like file delete, file run hide, file run normal, file delete, file rename. So these are the commands that the bot would receive. And this is apparently the function where these commands are being parsed. Furthermore, we saw other nodes like this one, which exhibited a system shutdown feature. So we get assign its own process the right to actually shut down the system, and then call exit Windows X to shut it down. And so we see a node which writes data to a file called log.log, which apparently is the logging function. And finally, we have a function which references a domain called paulpierce.3322.org, which apparently is parsing the domain where the sample potentially connects to. So without any detailed knowledge of the binary, we can see like we can get a certain idea of what is about to happen within that binary or what its intentions were. Another example from a different binary where the functionality wouldn't be contained within one node is this one, where up here you might not be able to see that appears the call next hook. So this is our Windows hook handler for a global Windows hook. Then we see this function where the APIs get keyboard layout and get key state are being called, and another function in the downside corner where get key state is being called again. So without any further knowledge about the binary, I would assume this is supposed to be a keylogger. Finally, here another example with a list of names of antivirus solutions. So you see this large node which has a list of antivirus products within there. So I would suspect that this binary is out to scan for installed antivirus products on a specific system. Well, this is something that could be performed in a benign sample. I would not assume that it actually happens within anything else than malware. So here we have another example of a binary which is suspiciously low on strings. You can see this here. So I tagged calls and strings in the graph by big C's and big S's. And there's a lot of C's in there, but very little strings. But what we do see is a lot of binaries which aim to download files from the internet and execute files from the disk. So you could conclude that this is an actual downloader. Okay, so what have we seen? You see these visualizations, they're a holistic view. You get a big overview of the binary. You still need a human analyst to do this. You have the plots, and then you spend a lot of time reading these plots. And that is not always feasible. As you can imagine, the examples I showed you were rather small binaries. But if you feed it, like, for example, a grown-up C++ application, you get graphs like that. So there you spend a lot of time actually trying to find your way through the binary. And it's actually not that easy to find connections between different nodes because there's so many edges. So here, the plotting doesn't really help. This is when the binary whispering comes in, finally. What we do in binary whispering is we search for specific API call gadgets, like I showed you before, like, for example, call gadgets that tell us there's key logging happening, or there's screenshots being taken, or there's files being written, or there's files being executed. These are the gadgets that the binary whisperer is searching for. This is being performed by looking into the graph and searching for nodes containing dedicated APIs. And starting from these nodes, around this area in the graph, the tool will search for these specific patterns indicating dedicated behavior. Again, there's a set of problems. Again, we have indirect function calls, which, for example, means that an API is initialized at some spot in the binary. This we know. We see the initialization there. And then the API is being called at a totally different spot within the binary. So this is hardly possible to parse. Also, there's this old issue with patterns. Like if we have call gadgets that are bigger, then we have lower chances to actually find the behavior we're searching for. If you make them too small, we find too much. And again, we need a human analyst to draw a conclusion. Now, what I actually mean with call gadgets, I have another slide here. Maybe you can read that. This is an experimental set of behavior gadgets that I would be searching for. This set can be extended. This is not at all conclusive. What I put on this text is just an example of what I would be searching for if I would be analyzing standard malware. So there we have, for example, the gadget for API loading, for dynamic loading of APIs. And we have the gadget for iterating processes. There is a gadget for iterating file system. And as the analyst keeps adding gadgets, he can actually search for these specific behaviors within the parsed binaries at hand. All right, now how does it look in practice? Here's the example again with that same sample I talked about before. And then this small sample, like the small graph that I showed you, you find a lot of gadgets already. There is dynamic API loading happening at 4 different locations within the binary. We have file system iterations at 2 different functions within the binary. There is altogether 5 threads being created by that single binary, and so on and so forth. So by just running this tool, you can get all this information at one glance. The tool itself, I intended to run rather fast. So building the graph based on the radar data for a standard binary might take up from a few seconds up to 5 minutes. So it's not light speed, but it's rather fast in manual analysis. And the analysis of the graph afterwards is really, really fast. So that's below 1 second for a usual binary to find out the specific gadgets. Here we have more examples. On top you see a random dropper, which, as any dropper, would download and write a specific file and execute this given downloaded file. And on the bottom you see another example of a binary, which I can tell you was about 250 kilobytes big. It was written in C++. It had a really big graph. It would show only one gadget of APIs that were being called within that binary. And if you look at that one gadget, this one gadget indicates dynamic API loading. So load library and get proc address are the Windows APIs you need for dynamically loading further APIs. So by looking at that result, I will conclude that this binary has something to hide. Something else we see within these graphs is straight down indicators for packed and obfuscated binaries. So whenever you feed something in there that the radar parser cannot properly disassemble and parse, you get a graph like that, like small, distorted, like not looking pretty. And this is usually a good indicator for packed or obfuscated binaries. Some more examples. This is also packed. This is even more packed. This is even more packed. There's another packed one. And this is my favorite packed binary. Right. So some binaries got something to hide. If you see a graph like that, like lots of nodes, a beautiful structure, no APIs and strings whatsoever, this should catch your attention. This is suspicious. This is why in the end I came up with binary metrics. There's a bunch of metrics which help me evaluate my graphs. So tell me, this binary is a GUI application. This binary is a keylogger. This binary doesn't show me any behavior at all. This binary builds a GUI. This binary might be obfuscated. This binary is definitely packed. And this binary doesn't show me any APIs or strings, like something is weird there. So I came up with a lot of numbers. Most of all because measuring things is fun. I like to look at binaries and know at one glance, oh, this is something interesting I should have a look at. Also, in binary analysis, we like metrics. Like, we like metrics a lot. We have no way to measure. Something is sophisticated. Something took a long time to implement. We have no way to say something is benign, something is very benign, something is possibly benign, or something is not benign at all. So far, in analysis of malware, we can differ between malicious and non-malicious. And this is not metrics. This is like very limited. So I decided we need more numbers. Now, the last thing I'm going to show you about this tool today. We can spit out a lot of information about the binary itself. This is the initial header, so you can get a lot of information to help you identify the binary. And furthermore, you get a lot of information to help you identify the graphs. So getting the function nodes and the amount of APIs and the amount of strings the binary, the graph possesses is one thing. But more interesting is the things that are missing. So if I get the graph, which is fairly big and fairly dense, and the graph has a suspiciously low number on references to APIs or references to strings, this is something that should catch my attention. Also, these kind of numbers are indicators for me that help me compare binaries, and even more, to help me compare distances between binaries. So if I have a set of binaries from which I know they come from the same author or from the same actor group, and I compare them with each other, and I find, like, over time, the added functions, the added functionalities, they change the strings that were referenced within there, I can watch an evolution of that specific binary and see what has changed over time, what has been taken from the code base, and what has been added to the specific code base. And of course, these numbers that I show on there that the parser spits out, they're extendable without end. So graphs are a nice data structure in many senses, but also because there's so many ways of measuring a graph. You can see how broad it is, you can see how long it is, you can see how dense it is, you can see how many disconnected nodes you have, you can see how many subgraphs you have, you can see how big the subgraphs are, how broad the subgraphs are. You can go through the graph with no end and can keep on gathering metrics. What did I do, for example, with my metrics? I came up with a fat node detection, which I call spaghetti code metric. So if you have like a bad software developer who puts all his functionality into like 2 different functions within the binary, you can spot him like at one glance because you see these big bubbles with like a lot of references in there. And you can say, like, this guy really doesn't know how to write software. Furthermore, the fat node detection helps us in finding the main functions within the binary. Main functions in the sense like the functions that reference most subfunctions, for example, or that reference most APIs, or that reference most strings. Furthermore, by looking at the strings and the APIs that are referenced within the node, we can see imbalances in there. So for example, we can see there's 20 functions, 20 APIs being referenced, and 0 strings being referenced. This is something that's rather awkward. What is more awkward, though, is if we see a lot of strings being referenced within the node and no API at all. So strings have to be parsed somehow. Either this is happening with local functions, or something is being weird. Either the parser failed in detecting strings properly, or this thing is obfuscated or tries to hide something else in one or another way. Finally, I'm almost done. Math. As I said, I'm not a mathematician, so I like to play with numbers. I don't always perfectly understand what I do. But there is some metrics that help evaluating a graph and actually showing at one glance how dense the graph is. What's more important, usually when you look at the visualization of a graph, it's fairly easy to spot specific areas that are very dense or specific areas that are very disconnected. Describing this in numbers is not all that easy. So I was super happy that NetworkX provided me with certain algorithms to find, for example, the average degree connectivity within the graph. This tells me how well interconnected my different nodes are within my graph. Furthermore, we have the out degree centrality. This metric tells you how many out degrees are to be found within your graph for your specific nodes, which tells you how disconnected the graph is in the end. So how many nodes actually have neighbors, how many nodes do not have neighbors to show. Also, we can evaluate how many loose nodes we have, how many disconnected nodes. This is a metric which I found out for usual C binaries compiled with Visual Studio should be around 20 to 40%. This is normal for a standard graph. If this number goes up for C or C++ binaries also up to 80 or 90%, you have a high probability that your binary is packed. Going on, of course, with the numbers that we connected before, we can count ratios. So there is metrics that provide the per kilobyte amount of API calls and the per kilobyte amount of strings. Interestingly, these numbers are fairly even in practice. So if you have a normal binary, these metrics will be between 4 and 6, or rather between 4 and 10 for normal binary. If this number is suspiciously low or suspiciously high, something is weird within the binary. All right, now just see my time is up. And I'm finished with my slides. So that was the Binary Whisperer. It's a side-time project. It's being a lot of fun. It is not yet ready for going into production. As I mentioned, if you want to use it, if you want to try it out, I'm happy to help you set it up and give you advice. And I hope you like the talk. If you have any questions, you can catch me afterwards, I think. Thank you.